And the nice thing about Verilog is it's not just for designing, physical logic circuits. It's a simulation environment, and you can describe your designs in a very abstract level. You can do functional verification of the design, and you can do that early in your design cycle. And in my case, I use this last principle quite a bit. I put in a lot of garbage, so I get a lot of garbage out. What can we do with Verilog? Here's some of the things that we can do, and we're going to go into a little more depth with these. We can model digital logic circuits. We can simulate and verify our digital logic circuits, and we can actually synthesize digital logic circuits. Now, like I say, Verilog, you can do all of this with Verilog. It's not just for the synthesizing. So in modeling our digital logic circuits, we can do that in a variety of ways. We can write behavioral level models, or RTL level models, gate level models, or mix level models. And I'll go into more details on that in a minute too. In simulating, we can write test benches to help us, and bus functional models that will help us verify our design and see that it's working properly. We're getting the right signals in and out, the right timings. We can do full timing simulation actually with Verilog if we want to. I'm not sure what the background of a lot of you are if you've had any Verilog experience, but this, of course, assumes you haven't had any. And one subset of Verilog is that we're going to learn how to do is write RTL code, and that's just a subset of the Verilog language. And with that RTL code, we can create combinational circuits like AND gates, OR gates, or combination of those, or we can create sequential circuits like flip-flops, and a combination of everything, all of those, combinational and sequential. Who should take this course? Well, if you need to synthesize, model, simulate, or verify a design with a high degree of confidence, then Verilog is a good choice for that. Or if you might need to use high-level practices and you don't have much knowledge, like I said, of Verilog. I'm going to take you all the way from the very beginning here, hopefully. Okay, so let's look at an introduction to high-level design. Most of you are probably familiar if you've done software. You talk about top-down designs or bottom-up. You can do both with Verilog. Let's say you have an overall system. At the very top level, we may have some system that we want to describe, and at a lower level, we may want to. That system may consist of several different board designs. Okay, such as in the HP SDR project. We've got several boards in there. You can use Verilog to help you not only design those or model those boards and maybe FPGAs, but to model and simulate the whole overall design if you wanted to. Or you could divide it to do a bottom-up where maybe you have individuals working on little subsections of the design, you integrate it, you work back up, or maybe you work it from both directions. But the goal is you want to have a working system the first time. So let's talk about a overall system, and you want to create a model, a Verilog model for that overall system. You can create, one way to do this is you can first start by creating what we call behavioral models. These behavioral models now, you could be able to describe the whole system. You can have, you'll have inputs and outputs and bidirectionals. You can model this system using the Verilog language at a very high abstract level. It doesn't have to start off at a gate level. So you can start at a more abstract level, which will allow you to actually create these models a little faster and then change it as time goes on. I'll show you how we're going to do that. Let's say that we started off and we had this overall model, and then we decided that, okay, it makes more sense. We'll break this thing down into 4 behavioral models. Instead of writing the RTL code, that's the subset where you're writing the real physical hardware, you could start off with these behavioral models, get things going a little faster, see that your overall system is beginning to work or is working, and then substitute in for those behavioral models an RTL model of the real physical design that you're going to use for, say, your FPGA. You could also one of the methods is you could substitute a gate level model. Now, you might get a gate level model from a vendor that has an IP for, say, a specific device, like maybe it's an RS-232 drive circuit, or a USB, or a DRAM controller, or something of that nature. You can also mix these models. Okay, you can use behavioral models, RTL models, gate level models, all within Verilog. Okay, maybe even something from a third party, like I said, IP, or a hardware modeler. You can join all these together and use them all. You can also, after you've gotten your design down to where it's down to the final gate level, or assuming you're going to make an FPGA or an ASIC or something like that, you can also, Verilog is good for doing what we call back annotating. You can back annotate timing. That is, you can put timing information into the model that actually is very close to what the real device is going to have. And a lot of vendors, even when you're doing FPGAs, you can back annotate this timing information into the model, and then you can simulate it, and you can see what the physical delays are going to look like coming out of this. Let's talk about the introduction to Verilog. In this presentation, you're going to see this kind of notation for like placeholders. You'll see this. Optional elements, you'll see things like this, and repeated elements, you'll see things like this. Let's look at the basic unit of Verilog, and it's called a module. Okay, and here's the syntax for it. We have module and end module, and for module we'll have a name with a semicolon after it. Okay, so this is a placeholder, and here's an actual example. Module, Aussie Janus, semicolon, and an end module, and this will be typically within a file. Verilog is case sensitive, so you have to keep that in mind. And the reserved words, let me back up, like module and end module, those are what we call reserved words. Those are in lowercase, okay? One of my guidelines, I would say, I'm going to present the syntax rules and a lot of that type of stuff as we go along, and I'm going to kind of give my own personal guidelines as to things you might keep in mind as you design. And one of them is to, when you create identifiers, and we'll learn more about that later, is to create them so that they have a meaningful name to them, not something that's cryptic, say like TR. Instead, use something like TX50 read instead of TR, and so on. Okay. Now there will be cases where, let's say you're taking one signal from one clock domain, we'll talk about that later too, into another clock domain, and you just need some flip-flops maybe to buffer it. You may just want to create a cryptic signal, that's fine, but try and create meaningful names and assume somebody else down the line is going to get a hold of this code and they're going to have to work on it, or you're going to get code from somebody else and you're going to have to work on it. You're going to want some meaningful names and comments throughout the code. Reserved words. You can't use reserved words as identifiers, okay? And in this case, module and end module. And Aussie Janus is our identifier here. Okay, so you wouldn't want to say module, module. The other thing, too, is it's case sensitive, remember. So in this case, these are actually 3 different modules, even though they look the same, because of the case sensitive nature of Verilog. In creating your identifiers, use characters upper and lowercase a to z, 0 through 9, and the underscore. And I'll show you where the underscore will be kind of handy for some other things too. But here's some examples here. Add 8, that's good. ATM underscore switch, that's a good identifier. And here's some invalid identifiers. Okay, so don't try and do anything like that. There are also what we call escaped identifiers. Now, personally, I never use these. These are things that are typically generated by some automatic Verilog generating code. So I would tend to just stay away from ever using them. But if you should see them, maybe in somebody's IP, some net list somewhere, just be aware that they exist. Indentation isn't significant. Line breaks aren't significant, but my guideline is it is very nice to see well-indented, well-organized code. In this case, yeah, you could write it like this in a single line, but it's much nicer for it to be like this. And we'll see more of this as we go on. It's also good that you put comments in your code. There's a couple ways you can do that. And this is, again, this is like C. /* begins it, / will end a comment. Or on a single line, you can put // So here's a couple of examples here. Verilog reads the input files as a stream of text. And the modules can be in several different files. They don't just all have to be in the same file. In fact, you don't really want them in the same file. It's preferable that you put them in separate files. Here's an example of what I'd say is bad, okay, and best. Okay, here somebody put module mod1 in a file, and they put the end module for it in the beginning of the next module in a different file, and then end module in a third file. I'd say that's bad. I'd spank somebody if they did that. And here's a couple examples that where you can put somebody's put two modules in the same file. That's okay, but in practice, I think it's best if you separate each module into its own file. Okay, the file names are arbitrary. So let's say you had a module that was called mod1. You could save it as file name, Fred, whatever. But I recommend that you use the same name as the module it contains. So here we see that I have a mod1.v, which contains module mod1, and mod2.v, which contains module mod2. I think this is a good practice. Again, these are my own, personal guidelines, and I've been doing Verilog since probably the mid-90s, and this tends to be, I think, probably one of the best ways to do things. Typically, for Verilog, compilation is performed in 3 phases. It does the source parsing and syntax checking, then hierarchical linking, and forward reference resolution. And you'll get different kinds of errors reported during different phases. Now, one of the things I'm going to need to work with everyone is, I'm sure everybody's going to have a different Verilog simulator, and I'm going to talk about a few different ones that you might consider later on in the lecture. Different simulators, compilers will give you different types of errors and stuff, and sometimes I kind of like to have 2 just to see if, when I'm having a difficult time understanding one of them, I could try it in another one and see what kind of results it gives me. Okay, there's a couple types of simulators out there. One's called an interpretive simulator, and in that case, the entire model is recompiled every time, and the compilation is hidden with the simulation. So I believe, and this has been a while, but I think Cadence's Verilog XL is one of them, and Synopsys VCS. There's also a compiled simulation, and the model is incrementally recompiled, and it compiles only what has changed. So, and the compilation is separate from the simulation. Now, I use ModelSim, and it's that way. And there's some others out there that do it this way too. Throughout these lectures, I'm going to give some lab material. I'm going to upload it. We haven't decided where it's going to be uploaded yet. We'll upload the lab material and a recording of these lectures on a website, and I'll post that and let everybody know as soon as I can. Basically, we'll have a Verilog directory, and it'll have the particular lab number in it. And in a subdirectory called solution, there'll be a solution to the lab that'll help you if you need it. And most of the labs come with instructions that describe the problem. And you're going to have to spend a little bit of time understanding the exercise before you begin the coding, which is similar to what you're going to do if you're on a job. There's also going to be some optional exercises that are included in which you can go into more depth and detail and get more practice. Okay, you can choose whichever Verilog system you want to go through these lab exercises. Here's a list of some of them. A lot of you, right now we're using the Altera ModelSim tools for the HP SDR project. However, the ModelSim is kind of limited in there. It's not my choice. I'd use the full version of ModelSim myself for what I'm doing. And this is something we kind of need to probably get together. I'm thinking maybe a lecture, a short 15, 20-minute lecture for the lab stuff might be appropriate, and maybe we can figure out which tools you might want to use. Now, for a free tool, This Icarus, you can look this up. It's a pretty good tool, probably for what we're going to do in these labs. I think it may work just fine. And there's also a free waveform viewer that you can look at the signals that you create with Icarus called GTK Wave. There's another one called Veritech. It's pretty good, but this one I believe is when I bought it, it was like $50. It was cheap. It does a good job though, so you might look at that one. So in the first lab, I want you to learn how to invoke a Verilog simulation and recognize some common syntax errors. We're not going to physically do the lab right now. In fact, as I go through this particular lecture today, I may talk about 2 or 3 labs before we're done, but you're going to do those on your own. Modeling hardware is only the application of Verilog. The modeling itself is done by writing software. So basically, you guys are going to become software designers in one sense. So let's talk about sequential Verilog. We're going to talk now about the always block. Okay, an always block is a program that is stuck in an infinite loop. It might seem a little strange at first, but you'll understand why as we go on. And it executes sequentially from top to bottom. Once the bottom is reached, the execution starts at the top again. So here's the basic syntax of an always statement. Okay, you have always and a statement. Now this is a simple statement. I'll show you what a compound statement is, but this is still the basic syntax for the always block. Okay, and this is how it just repeats over and over. So executing a single statement indefinitely definitely isn't useful. A begin end block makes several statements look like a single statement to the compiler. So if we go back, it's still this same basic structure, except instead of a single statement, we've made it into a more compound statement, but it still looks like a single statement to the compiler. So now, and note my grammar here, this means the statement can be repeated. Okay, so we have multiple statements between the begin and end. Okay, and here's an example. So now we can start to do something useful with it. And an always block goes inside a module. That's where you're going to place it. You have to place it inside a module. So here's an example. Okay, now another block is called an initial block. And it's similar, but it's a program that runs only once. And it executes sequentially from top to bottom. And once the bottom is reached, it's done. That's it. And we'll learn whether that's useful. And 2, it can have a compound statement with a beginning end. And it too goes in a module. Okay, let's look at a simple write statement. This is used to display a message to the standard output. And message string must be on a single line. A new line must be explicitly appended. You can use a /n to insert a new line character in the string literal. And so here's the syntax for write and an example. Okay, it's the hello world. We've all seen that in C. The finish statement is used to abort a simulation, to stop it. And simulation stops by itself if there's nothing to do. In the second lab, you're going to learn how to work with always and initial blocks and use this finish statement. So you start getting a feel for this. In the digital world, we're used to thinking of ones and zeros. Well, for Verilog, not just ones and zeros, but also Z and X, high impedance and unknown. So Verilog is known as a 4-valued logic system. And we're going to talk about how you use these X's and Z's besides just the ones and zeros. So valid digits are 0, 1, lowercase and uppercase z, a question mark, upper and lowercase x. There's 1 bit per digit. And it's 0 filled to 32 bits. We'll talk more here about this. It's filled with 0x if most significant bit, and not sign extended. So let's start taking some looks. Here's the syntax. Let's say we want to describe a binary value. So here's the syntax right here, and here's some actual examples. We go tick B0, and that's equivalent with to 32 zeros. Okay, the default here is going to be 32 bits for Verilog. Tick B0 is basically extended to 32 bits of zeros. And now here's another example where we have tick B10XZ. So we see the 10XZ, and then it's extended to 32 bits also. Okay, let's look at decimal literals now. And you can use digits 0 through 9. And you cannot use X's or Z's in the digits. And there's no bitwise correspondence like there was in the last one. Head 2 is 0 filled to 32 bits and not sign extended. So here we have tick DZ and then one or more digits. So here's an example. Tick D7. In binary, this is what it would represent. And similar for tick D12 and tick D1. You can use hexadecimal literals, and in this case you use digits 0 through 9 and A through F and Z and X. And there's 4 bits per digit since it's hex. So again, here's the syntax and some examples. So tick hex 1F, this would be the binary representation of it, 1 and then F, those 4 ones there. And then tick hex 17XZ. So remember, these represent 4 bits and these represent 4 bits. So this over here would be the binary representation of what you've written there. Okay, so let's say we don't want just 32 bits all the time. We want to create something that's a little different. Okay, this method that we're going to do now is good for any of those literal bases, whether it be binary, hex, octal, whatever you're going to use. Yeah, and sometimes these extra bits are truncated, and you might get a warning by the compiler, but that's okay. And let's take a look at the syntax here. Here we see in front of the tick B or octal or decimal or hex, we put a size first, and then we'll put our digits. So in this example, you know, this would be good time because I do need some feedback. Is there a way we can turn audio on in case I can hear some people? Anyway, go ahead. And in this example here, 1 tick B1, can somebody tell me what's the size of this binary literal?
Yeah.
So in this case,
Kirk,
we have 32.
Sorry to interrupt. Can you back it up a little bit? I was trying to unmute everybody, but it got extremely noisy really fast. So
okay, we won't do
the best
that
way
then.
to do it would be, yeah, I think the best way to do it would be to maybe send a chat to me, and I'll open it up to that person if you have questions. We can do it individually.
Okay.
So,
or what if I ask
I'm going to mute
questions?
myself again.
What if we ask questions and they just respond in the chat?
Okay. Yeah, you can see.
Can they do that?
Good. Yeah, I think so. Yeah.
Okay. Well, I'll try it. If not, if I don't get any responses, I'll keep moving on. Okay. So in this case, the size is 1. Okay. So it's just a single bit, and the value is 1. In this case, because we didn't specify a size, it's 32. That's the default. So here's the binary representation. And in this case, we specify that the size is 8 bits, and it's a hexadecimal number, F0F, and here's the binary representation. Notice that we don't get this extra F because we said the size was 8, so it truncates it. And you may get a compiler warning about that. And here are some other examples, and I'll let you look at those. If anybody would like to send a chat to me if they've got a question along the way, I'll try and answer here. Because it's pretty much dead silence on my end because we don't have audio turned on coming back because Mike said got to be a little noisy. So, but I will try and monitor the chat if somebody wants to ask me any questions as we're going through here now. Somebody asked if 32 bits is an absolute limit. No, it's not. We're going to talk about that. That's just the default. That was pretty much the standard in Verilog 95, but no, you can go much wider. And in fact, one design that I was doing not long ago, I was doing a DDR2 DRAM controller, and my internal bus was 432 bits wide. So hopefully that answers it. Somebody asked if there's fractional notation. No. We're going to get to some more types as we go along. Right now, we're just looking at the binary, octal, and hex and decimal type. But I'll go ahead and continue on. Hopefully, I'll answer some of these questions. Okay, integer is another type we can use, and you can use digits 0 through 9, and it's a 2's complement 32-bit integer. And here's the syntax and some examples. I think these are probably pretty straightforward. You can also do what we call real literals, and again you use digits 0 through 9, and it's double precision 64-bit floating point. And here's the notation for it, the syntax. Okay, so this probably looks fairly familiar. And some simple examples. Okay, let's talk about logical values now. Any non-zero value is true. Anything else is false, including X and Z. So let's go through examples. So let's take a look at this first one here. And we have 1 tick B0. So in this case, the logical evaluation of this value is false. In the next one, it's true because it's non-zero. However, in the next one, it's false. Oops, sorry. In the next one there, the 1 tick BX, it's false because it's including an X, okay? This one, of course, is false. This one is true because it's non-zero and it doesn't have an X or Z. This one, the next one is true because it has a 1 in there. And the next one is false. Okay, let's talk a little bit about bitwise operators. There's what we have what's called a bitwise not, and you put a tilde in front of the expression to specify that. A bitwise and, you will use an expression with this ampersand symbol between the two expressions, and that will represent a bitwise and. Similarly, a bitwise or, an exclusive nor, either one of these. And here's some examples. So tilde, 1 tick B0, that's a single bit of 0. The bitwise not of that would be a 1 tick B1. Okay? Now, here's an example where we're doing a bitwise not on these 4 bits. So this one becomes a 1, this one becomes a 0. An unknown still becomes an unknown, and also a Z becomes an unknown. Now here's an example where we're doing a bitwise AND. So what happens is this bit right here, the 0, gets ANDed with this bit right here, 1, and the result is 0 right there. And then that 1 gets ANDed with that 1, it becomes a 1. And this X gets ANDed with a 1, and so that becomes an X. Does this make sense? Similar for this one with a bitwise OR. So 0 and 0, that would still be 0. And then 1 and 0, that would be a 1. And then an unknown ORed with a 0 is still an unknown. Okay. Then we have something called reduction operators that can be used in Verilog. And the syntax is like this. An AND reduction has the ampersand in front. An OR reduction has this bar in front. And an XOR reduction has this symbol in front. So let's look at some examples here. Let's do a bitwise AND reduction of 3-tick B001. So basically, you AND each of these bits together. And in this case, of course, the result is 0. And it's a single bit, the reduction operator, the result of it. And in the next one, I keep losing my mouse for some reason here. You AND each of these 1s together, and the result, of course, is 1. And in the next case, we AND each of these together. You AND a 1 with an X, you're going to get an unknown. So the result here is going to be an unknown. And in this case, anytime you AND 0 with anything, the result's always going to be 0. It doesn't matter whether it's unknown or 1 or Z or whatever. Oh, previous, sorry. Similar, we look at the OR reduction operator. The result again is a single bit. And you OR these 3 bits together, that's 1. You OR these 3 together, that's 0. You OR these 3 together, because there's a 1 in there, doesn't matter what the others are, the result's going to be 1. Similar, in this case, you OR anything with an X. Well, you OR 0 and an X, you're going to get an unknown. If you OR a 1, it may be a little different. It would be a 1. What about X01? Okay, that you're ORing those. So in that case, since you know you have a logic 1, doesn't matter what you OR with a logic 1, you're still going to get a logic 1. And then here's another case for exclusive OR, and I'll let you look at that more in detail as you look at the recording of this lecture. There are also vector operators. And again, in vector operators, you have 2 expressions here. For the logical shift left, here's a good example. So we have 1, 0, 1, 0, and we shift that left 1 bit. We're going to lose this most significant bit, and it's going to shift in a 0 on the least significant bit. So that's why we get 0, 1, 0. Similar, if we shift right two bits for this 1, 0, 1, we're going to wind up losing these lower 2 bits, and it's going to shift to 0 in on the most significant bit. Now, we have something that's called a replication operator, and I did not put that one in here. We'll talk about that later. These are some of the operators that you're going to use quite a bit. Well, here, I'll talk about the concatenation one, because I've got to finish here before too long. Now, in this case, you use curly brackets in the Verilog code itself, right here at the beginning and at the end. And you have some items separated with a comma, like we show up here in the syntax. So these curly braces are part of the Verilog syntax in this case. And here we have 3 bits with a value and a single bit with a value. And by concatenating them in this manner, you'll get 4 bits. And hopefully that's fairly obvious. Let's go ahead and talk about replication too. We got time. The replication operator, basically, here we have a value, whatever we put in here, In this case, we've put in a 2-bit value of x1. And this 3 says to replicate that 3 times. So we wind up with a 6-bit value of x1 repeated 3 times. And this can be very useful in things. Also, we have standard arithmetic operators. These are pretty straightforward, I think. Add, subtract, multiply, divide, modulus, 2's complement. I'm not going to say too much about those. We have relational operators. We have a couple different types of relational operators. We have equal, not equal. That's one group. And then we have what they call identical and not identical. Okay, and notice the difference between an equal and an identical. Okay, we have an extra equal sign in here. Similar for a not identical. Okay, and when you use the identical, the x and the z bits must be identical in order for it to evaluate properly. So let's take a look at some examples. I'm going to ask Mike how much time we have left now. $15 minutes. Okay, hopefully I'm going to get to a break. Like I say, this is kind of new, so I'm going to have to learn how to tailor this for our web time instead of a classroom environment where I'm going all day long. So here we do a comparison of 3-tick B000 with 3-tick B010. And of course, those aren't equal, so that's false. So that's kind of obvious. And the next one, I think that's kind of obvious too. So notice that the result of this evaluation is a single bit. Okay, 1-tick B0, 1-tick B1. Okay, now in this next one, we're doing a 3-tick B0x1. Is that equal to 3-tick B0x1? And why do you think the answer is false? Anybody have an idea? What does x actually represent? This might be an easy way to think of it. X could be, either or. It could be a 0 or it could be a 1. So, it could be, in this case, maybe the x, what if it were a 1 here and a 0 there? So it's not, so this evaluates to false. So, yeah, x is unknown. That's why. Okay, same thing here. So this is where the identical and not identical operators come in so that you can compare x's and z's on a bit-by-bit basis. So here, we can do that compare with using those. You have to think about this. It's not maybe real intuitive at first, but as you play with it, try doing some simulations with it, you'll get kind of used to it. And this is all because we're using this 4-valued logic system. Sometimes you're going to just have to refer back to a book or a manual because you're not going to remember all this. I don't all the time. So I have to refer back to make sure I'm doing this correctly. And maybe some of you catch on quicker than I do. We also have relational operators, less than or equal, greater than or equal. I think those are probably pretty obvious. Let's see, somebody asked about Z. I assume that's back in this last one. Yeah, I think that would also apply to Z. Probably find a good textbook. I would suggest that find some Verilog textbook out there that you can refer to. And typically in the back of the textbook, they're going to have syntax, or maybe you can find something on the internet and just look at some of these rules. I mean, going through a lot of these syntax rules, this can get, for me, I might be sleeping right now if I were listening to the lecture because sometimes it can get a little boring, so I'm sorry about that. But we have to get through some of this. You have to at least know to go look it up. If you can't remember it, just go and look it up, until you start remembering these kind of things. And some of this may be just a little boring at times. But I want you to realize all the different types of operators, and we'll get into more on what you can do in each one. You also have logical not, logical and logical or. Okay, and logical not. Okay, what's the evaluation of this value, this non-zero, right? Okay, so you can think of that as true. So the not of that would be false. Okay, we're getting close on our time here. And so these are some examples that the logic, let's go ahead and go through some of these. So let's look at this one here. Here we have 3 tick B001. So this is a non-zero value, and we're ending with another non-zero value. So the evaluation of this expression in terms of true and false would be true. This one would be true. So the result would be true. Okay. Whereas, now that was a logical and. Now let's look at a bitwise. Remember, a single ampersand is a bitwise and. So in this case, the result is 3 bits, not a single bit, but 3. Okay. So you got 0 and 1 and 0, 0 and 0 is 0, and then 1 and 0 is 0. So you get the final result is 3 tick B000, in which case that's false. Similar here for doing operations with x. You can see what happens. We got 1, 0x, and we're doing a logical and with x01. So the evaluation of this is 1, because 1 and doesn't matter what the others are. So the evaluation of this is 1. So the result is going to be 1, which is true. Whereas with the bitwise, similar type result, you get 3 bits, okay? And of course, that's false. And then a similar type thing going through a logical OR versus a bitwise OR. Just remember, and you can look this up, just remember the difference. There's a difference between a logical OR and a bitwise OR and how they evaluate. Okay, a lot of this stuff is about how these terms evaluate, and you're just going to have to do examples and try them out just so you get a good feel for how they work. We have in Verilog what's known as a conditional operator, and you have 3 expressions. Okay, after the first expression, you have a question mark. So if expression 1 is true, okay, or the logical, or the evaluation of that expression is true, then the result that you're going to get is expression 2. If expression 1 is unknown, then the result is x's. Otherwise, the result is expression 3. So here we have the first expression, and that would evaluate to a true, that value, because it's non-zero. So the result over here, 1, would come from this expression 2. And in this case, the expression 1 is false, so we're going to pick the third expression, and so that value of this result is 2. Now, in this case, it's unknown, it's x's, okay? So then the result is x's. It's neither one of these. So just bear in mind how that works. We also have operator precedence, okay? And there is a highest to lowest precedence order. And you're not going to always remember this either. So just remember that you need to check it out. Or if, let's say you're doing, an and of a couple values, and then you're comparing to see if that's less than some other thing, you may want to just put parentheses around things until you get used to the precedence of everything. So just remember that there is precedence and that you may need to watch for it when you're coding. So, how are we on time? This may be a good place to stop and ask if there's any questions before we get into registers. Yes, it's good to use parentheses. I use them a lot just to make sure, and then you don't go astray. So I do a couple of expressions, whether I'm doing logical and or whatever between 2 expressions. I'll put parentheses around those, and then I'll put parentheses around some other things, and keep things kind of separated for sure, and then I don't have to worry too much about the order of precedence if I just put parentheses around things. There are going to be quite a few of these lectures, and like I say, there's a lot of material we just have to get through in order to do anything useful. So I hope you can bear with these lectures. There's going to be quite a few of them. Anybody have any more questions? Okay, if you want to open it up to voice, that's okay. We can try that, see if it doesn't get too noisy. I'm going to ask Michael, did my voice come through clear enough on this? Is this going to be a good medium through which we can continue this series? Reference book for Verilog. There are a lot of reference books out there. Let me see if I can grab one. I have one here that I kind of like. It's a hardback. And I've got different ones. Let me pull it off my bookshelf. And I kind of like this one for reference, but I haven't looked at a lot of them. This is called Verilog HDL, A Guide to Digital Design and Synthesis, and it's by Samir Palnitkar. I'm not sure if I'm saying that right. SAMIR-PALNITKAR. And it has some pretty good reference material in it. 90 minutes, okay. The next lecture, I'd like to at least do 2 of these lectures a week. I'm also thinking that it would be nice, especially when setting up to do your labs. Some of you may not have ever set up a Verilog simulator, may need some help. Maybe I have a short 20-minute lecture just to help people with lab material or something. Let me post the name of this book here, just if anybody's interested. There's a lot of them out there. Guide to, I'm typing this in right now. That's one of them. I have that. I kind of use that one. Now, some of you, you may, I don't know what all your purpose is. It'd be nice if those that attend would kind of send me a short, maybe a little short sentence or 2 about what your interest is in Verilog, kind of what you, where you see a use for it and what you do. I'm always just kind of curious as to how people are going to use it. Some of you may go into design. Some of you may go into verification. If you're writing test benches, we haven't talked about that yet, but there's another good book out there by Kluwer Academic Publications. It's called, and I knew this guy, Writing, let me type it in, Writing Test Benches. Functional applications. HDL models by okay, that's I'm sending not to everybody. Okay, I need to current version of Xilinx. Okay, I'm not sure what was meant by that question. I missed that. I'm not sure about the built-in ModelSim simulator that comes with Xilinx. If it's a standalone thing, that'll be great. I haven't used it, so I don't know. I've used version all the way from version 6 of Xilinx ISV tools up to current like 10.2, but I always use ModelSim as a separate tool. So I've never tried the one that they ship with the tool. So maybe that's something I can look at. Okay, a walkthrough on the Icarus simulator and GTK waveform viewer might be helpful if this is what we're going to use for the lab. You're welcome to use anything you want for the lab, but yeah, maybe it might be a good thing. I'll look into that and see what I can do for, maybe we can have a quick little session for those wanting to use that for the lab. You can pretty much, it's not really going to matter if you use different Verilog simulators.